Okay, so this is another chapter. This is the start of another chapter of our discussion. So we already done with the transfer functions. So you already know how to derive the transfer functions of different systems. Either it's electrical system or mechanical system, or it can be both combination of electrical and mechanical system or electromechanical system, rotational system, and so on. And now, in the next chapter, we will be talking about the pictorial representations of uh, systems that we derive from the previous chapter. So there are two. The first one is the block diagram. The other one is the signal flow graph. So first, we talk about block diagram. Block diagram, it's the representation a pictorial representation of a system, and it composed of a block. This block represents the transfer function. We can call it G. This is the transfer function that we derive in chapter 2. So it can be, if this system is an RC system, an RL system, or any type of system, you already know how to derive this G here. And in this system, we model the system. We have, of course, an input, and we have an output. So these arrows, this represents signals or stimulus. Can be input signal or output signal. So it depends on the direction. So the direction of the arrow represents the direction of the signal. So in this case, this signal here is the input. So we can call that one R. We can represent that R. These are all in S domain, by the way. And for the output, we represent it with letter C. This is a simple block diagram. And this type of control system, there are generally two types of control system. Control system. The first one is is a very simple system, just like this one. This one can be considered as a control system. We call it an open loop system. Open loop system. Open loop control system. So what is open loop control system? An open loop is straightforward. This means the output or the input doesn't care about the output. So you apply an input, whatever the output is, I don't care. The input, it doesn't matter to the input. Why? Because for the other one, the closed loop control system, closed loop, or we call this one the feedback control system. So there's a feedback. And this is mostly all of the control systems are a feedback control system. Rarely, we don't use the open loop. We only use them if we need a very simple control system that's like this one. A closed loop in block diagram. So you have, this is the block diagram. This is the block transfer function. You have the output, and this is our input. Then we have a point here, and we have another block here. We call it H. This is the transfer function of the feedback. And the signal will be coming from the output, and it goes back. It goes back to the input. This can be plus or minus. And this is a closed loop system. This is a very simple closed loop. They call this one the canonical form. Canonical form of a control feedback control system. So there's a feedback. Where's the feedback? This is the feedback. They call it feedback. So what's the difference with the open loop? This one, you have a connection between the output and the input OR. So there's we call this point here, we call this the summing point. Summing point. Well, this one, this point here, we call it the takeoff point. Takeoff point. So what's a summing point? What a takeoff point? A summing point is Some books uses, if you see, you saw a symbol just like this one, this is a summing point. So if we have more than two signals coming in, then we have here an output. So let's say this is X, this is Y, and this is Z, and this is W. Now a summing point, if these are all positive, plus, 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 then we can solve for W. W is just equal to just X plus Y plus Z. That's why it's called the summing point. So if this is minus, then minus Z. This one is also minus. So it depends on the sign here. So it's just like KCL. If you remember KCL, Kirchhoff's current law, leaving and entering the node. This is a summing point. While the takeoff point, it's a different case. So if we have here, let's say this is the point, then we have a signal coming here, let's call it X. Then the signal is divided into 3 signals. So if this is a takeoff point, and these 3 are all connected at this point, then this is also X, and this is also X, and this is also X. So this means they are all X, because they are all connected to a signal which is X. So this is a takeoff point. So this is a take-off point. This is a summing point here. Summing point. Now, why do we need to study this one, the block diagram? So we already discussed how to model the system. Is it enough for us to just derive the transfer function of the system? Then that will be the model of the system. Now, if we have an example here, if we have a DC motor, so a DC motor is this. It has a resistance and inductance. Then if this is the motor, then this is the shaft of the motor. Now if we have an input, the voltage here, we have a voltage, then this motor will rotate. So our output here, let's say we need to control omega, or the angular velocity of this motor. We need to control the speed of the motor. And to do that, in machinery, in electrical machine designs, how do we control the speed of the motor? We just need to control the voltage, input voltage of the motor. The voltage is proportional to the angular speed, or the speed RPM of the motor. So this is a basic law in electrical machine designs. So now, if we adjust the voltage at this input, then we can adjust the speed. Now, if our input now is I want the speed of the motor up to this speed, let's say 2000 RPM, 1200 RPM, or whatever. That's our input. That's why we call our input here, we call it R, because this is the reference, or it's the setting. Sometimes you call it S. It's the setting, the reference setting, or that's what we want. Our input is what we want, while our output is the actual volume. So we compare them. So if they are equal, then we already reached the reference, or the input. Now, we have a voltage here, a source voltage. Let's say we have a constant, a battery, and this voltage is constant. It has a voltage V. So plus, minus. Now, how can we control the voltage of this DC motor if we have a constant voltage? So we need what we call a DC-DC converter. DC to DC converter. So what is this? This is they also call this one the DC transformer. So if we, in transformer, AC transformer, we step up or step down the voltage using a transformer. It's easy to step up or step down the voltage if you are in AC. But in DC, it's a different story. So we need a DC-DC converter. This is just an electronic. It's a circuit. It's a circuit, and it depends on the application. There are different topologies for this one, DC-DC converter. It can be a back, a boost, a back boost. So, for example, mostly we have just like this one. We have a diode here, or if we have a back is a step down DC-DC. So if we have a MOSFET somewhere here, a switch, then I have an inductor, then if this is a diode, then you have a capacitor, a filter here. So this is your input, V input here, and we have your V output here. So this one is an example of a back converter, DC-DC converter. It step down the input. So this is a back. But if you want to step up, we use boost converter. So you just swap the MOSFET. So the diode will be somewhere here. So here will be the inductance. Then we have this will be the MOSFET here. Or it can be any type of switching mechanism. It can be IGBT or so or whatever. And here is the diode. So this is the output. B output. Then we have the input here. So this is a boost converter. So what does it does? It boosts or step up the voltage V in into V out. And the gain depends on the parameters, the inductance and the switching frequency of this MOSFET or the duty cycle. For the combination, the inductor for a back boost. So this one is a combination of the two. It can be step up or step down. So the inductor will be in the middle. Then here we have the MOSFET or any switching mechanism. Then we have the diode here. And we have a capacitor. So this is a back boost. Example of a back boost. A simple back boost. So we have input and we have output. Then there are many other different topologies for a DC-DC converter. It depends on the application. But you will all study this one under industrial electronics. For your subject on industrial electronics, you can ask your instructor to explain more about these circuits. Now that we know how to vary the voltage, so that we can vary the angular velocity of the DC motor, and we will connect this. So there will be an output here, plus minus output of a DC-DC. Then we will connect this one here and connect it here. Now that we know how to vary the voltage, the problem is this is an open loop system. This is an open loop control system. We adjust the voltage. We can also adjust it. It depends on the duty cycle here, and the control part of this one is usually we use most DC-DC converter. They use potentiometer. We already know how a potentiometer work. It has 3 terminals, and you just need to rotate the potentiometer. You adjust. It's a variable resistance. You adjust the resistance here, then you can now adjust the voltage output of the DC-DC converter. Then it depends on the angular speed that you want, angular velocity that you want. But if I rotate this into a 90 degrees or 30 degrees rotation, then there will be a voltage here. But how do I know if the rotation of that, because there's a different Usually we have here, if this is 1000 RPM, 2000 RPM, and so on. So these are scale of the potentiometer that you want. What do you want of the DC motor, the angular speed of the DC motor? So this is an analog example because we use analog to control it. You can also use digital controls by using, you can use keypad or something, or touch screen and so on. But this is the conventional way of doing this. So if I just adjust this one into 1000 RPM based from the scale, but the problem is it really 1000 RPM? Is it the angular speed of the DC motor, is it really 1000 RPM? How can you say that it's really 1000 RPM? So this is an open loop. This is the problem of an open loop system because the input doesn't care about the output. We don't look at the output. But if you are the operator of this one, you can check it by using a tachometer. You measure the speed here. If it's really 1000 RPM, then you stop the rotation. It's really accurate 1000 RPM. But in reality, we don't do that. We don't, if the application is, the motor is inside something, you cannot access the motor, and it's a problem. So what we do is, instead of an open loop system, we make it a closed loop system. So how do we do that? We need to put here a sensor, or we call it the transducer. Specifically, this is a sensor. A sensor. So what type of sensor? Tacho generator or tachometer. Tachometer. A tachometer is basically a generator. It's just a DC generator. So if you rotate the generator, if you rotate the generator, you have a voltage. So the voltage is again proportional to the speed of the rotation. The faster the rotation, the higher the voltage output of this tachometer or generator, tacho generator. So there's an output voltage here, a DC output. Now how do we take, what will we do with that output? This is a signal, this is a voltage, so we can consider it a signal. We use that so that we can base our voltage from that. So if I set this one to 1000 RPM, so we need to have a 1000 RPM at this one. So when will be when will the tachometer give me a 1000 RPM? So what voltage should I take so that the speed of the motor is 1000 RPM? So we need to connect that. And what we do usually is we use a operational amplifier. So minus plus. We need the summer. So how do we do that? So for example, a summer, you have two inputs, two voltage inputs here. And these inputs, now what we want is, if I adjust this, you have a voltage somewhere here. Then I have here the potentiometer. Then this voltage is connected to this one, positive. So by adjusting this potentiometer here, the voltage will also adjust. So if you have a voltage here, so, let's call this one B ref. This is our reference now. So if I want it to be, let's say the tachometer is a sensor that if the speed is 1000 RPM, it's equivalent to, let's say, 10 volts. The output voltage of the tachometer should be 10 volts. So if I will set this one in this potentiometer, I adjust the potentiometer until it will become 10 volts because I want 1000 RPM. So I need to have a potentiometer or a voltage here that is exactly equal to 10 volts. Why? So that my speed is actually 1000 RPM, exactly equal to 1000 RPM. Okay? So now, this one, so this is the positive here. I will connect this point here to this point. Then the input here will be the voltage from the tachometer. And it will compare the voltage, the voltage reference and the voltage coming from the tachometer. So if they are equal, so this is, if this is, let's say this is this minus, okay, so that it will subtract the two. Then the output here will be B ref minus V tac. And if this is equal to 0, this is exactly equal to 0, the output here is exactly equal to 0. What does it mean? This means that VRF is the same as the voltage across the tachometer. So if that becomes 0, then if I connect it to the DC-DC converter, I will tell the DC-DC converter to stop adjusting the voltage. Okay? So if there is a difference, then the DC-DC converter need to adjust until the difference here is 0. So if I set it here, I rotate the potentiometer here to 1000 RPM. So the output voltage here should be equal to 10 volts. Now, the DC-DC converter we need to activate this one until it reaches 10 volts so that the voltage in the DC-DC or in the DC motor will also be equal to 10 volts. And if it's 10 volts, then the speed of the DC motor will be exactly equal to 1000 RPM. So this is a complicated example, and this is what really, in real control system, this is the real components of a real control system. So if you look at these different components, it's not just one component. So what we did in chapter 2 is we just model each component. We model the potentiometer. We model an operational amplifier. We model an RLC circuit. We model an electromechanical system or the rotational system here. So these are different transfer functions. So we have a transfer function at this part. This part is one transfer function. The potentiometer is another transfer function. The DC-DC converter is another transfer function. And this DC motor is another transfer function. And also, the sensor is another transfer function. So these are different transfer functions. Now, if we draw the block diagram of this one to simplify this complicated circuit, we need to draw it into the block diagram. So how do we do that? How do we draw the block diagram? First, what do we want to control? We need to control the DC motor. So this is the DC motor. This is the transfer function of the DC motor. Then, what's the input and what's the output of the DC motor? So we have, your output is the angular speed or angular velocity, while the input is we apply a voltage here, V. So let's call this one, it's not a different V here. Let's call it Vm, the voltage of the motor. Then, the voltage of the motor here, that's the input. It will be connected to a DC-DC converter. So we have here a DC-DC converter. DC-DC. So the output of the DC-DC is Vm. Then there's a voltage coming from a source from the DC. We don't need to draw that. It's just, it can be not part of the system. It can be part of the DC-DC converter. Then we have another signal. This red signal coming from the operational amplifier. And that one is actually a summing point. So remember, a summing point, it adds or subtract two different signals, just like what this one did. So it just subtract Vref and V of the tachometer. So we can use that. So it adds two signals. And what are those signals? This signal coming from the VRF and the signal coming from the voltage of the tachometer. And then VRF is connected to the potentiometer. So we have another transfer function here. The output of the potentiometer is a voltage, while the input is what? It's the angular position, the rotation of the potentiometer. So our input is the potentiometer, and this potentiometer, it represents the scale. If you remember the scale, if this is 1,000 RPM, 2,000 RPM, and so on. So there's a different angle for a different speed. So if it's 1,000 RPM, so this is the angle theta. If it's 2,000, and then this will be the angle theta, and so on. Then you can also add that here if you want. You add the transfer function if that the equivalent of this scale. Then our input will be the actual angular speed that we want. W reference. This is the actual value of the W. So this is the scale. So that our input here will be theta. So this will be theta here. We rotate the potentiometer, and the potentiometer will be resulting. The output of the potentiometer will be a voltage. Then that one will be added or subtracted. This plus is minus. So Vref minus V. Vref minus V of the taco generator. And this is actually what we call E. It's just the error. It's the difference between the actual and the input. Then this one, the taco generator, or the voltage, is actually the output of the sensor taco generator. This is the output of the taco generator, the tachometer. Then the input for the tachometer is the rotation. It's a generator, so the input is mechanical energy. And that rotation is the actual rotation, W. Actual. So we have a takeoff point here that will be the input of the taco. And the output of the taco will be a voltage that will be subtracted here in the summer or in the operational amplifier summing point. Then if there's a difference, we adjust the voltage. So we have a voltage here, V, our input here. And this will be the block diagram of that system. So if you look at this block diagram, this is much better than looking at this circuit here. So if you have this one, you can actually relate the actual and the reference. So you need to solve the output divided by the input, W actual divided by W reference. And this is the total transfer function of the whole system. Remember, of the whole system, including all the components. So what we did in chapter 2 is we just solved for the individual transfer function. Now, what we are doing here in chapter 3 is we are combining them into a system, into a whole system, into a control system. That is the definition of a control system. This is it composed of different components that is being controlled. So, block diagram is significant, especially in control system. But the problem is, how do we solve this one, the transfer function? If we can draw the block diagram, we already know the block diagram, but how can we determine the transfer function of the whole system? And that will be our next topic for the next video. We will be discussing about how to solve for the transfer function of the canonical form. We will reduce this type of block diagram into just a simple block diagram into a canonical form, just like this one. So if we are in a canonical form, we can determine the actual transfer function. Okay.